Exactly what the title says, making chips cry to improve lives. So, what is this? Well, it's the core of a potentiostat, which is a device that measures the potential between two electrodes. And while that may sound boring, and honestly not too much different than a multimeter, it actually has serious potential, if you get what I mean. Anyway, here's the circuit diagram in general of a potentiostat, and now let's talk about improving lives. So, blood tests. They are costly, inconvenient, and there's limited access in remote areas. This, all in all, makes them rather slow and could be improved upon. This potentiostat can run 18 tests in parallel and up to 20 with modification, making it way faster and more convenient than traditional methods. How? CNTs, carbon nanotubes. Molecules attached to CNTs, sort of like antibodies attached to germs. And what this does is it changes the capacitance and impedance of each carbon nanotube. You can think of them like little capacitors. And then using AI, we can back calculate from these capacitance and impedance measurements to figure out which molecule has attached to the CNT. And this allows us to detect which chemicals, which antibodies are present in blood and other chemicals. And that's really powerful because it gives us greater insights into what we're looking at and patient health. On to how I got started on this project. So I stumbled across the Berkeley Nanotechnology Lab website and thought the work was really cool. And I asked the professor if I could help, and it turns out he had just the thing for me. So, why do we need a microcontroller? Well, we can use the ADC, analog to digital converter pins, on a microcontroller to read the data from a potentiostat. That's what allows us to do the blood tests. Now, the problem is that the previous microcontroller, a TI Tiva-C, was simply too slow. We just couldn't get the data out fast enough. Now, an obvious solution is a faster microcontroller, and that is a TNC 4.1, shown in the bottom picture. And what I need to do is I need to get these 18 ADC pins on the TNC to sample at 10 kilohertz. And we need to do all of that in real time. So essentially, we need to send 180,000 numbers per second. So anyway, let's get on to early testing. After a bunch of work, I got this code, which is honestly pretty simple. It reads the sensor value and sends it out. It's not too complicated. And it sends the data out as raw bytes. So let's deploy it. As you can see, it uploads pretty nicely, and if I go to serial monitor, I see a bunch of nonsense, which, as I'm sending raw bytes, is exactly as expected. So then I do some more testing, and I show it to the professor, and he loves it. It's great, okay? Then he asks me to bump the resolution from 10 bits to 12 bits. So let's go and do that. 12 bits, then we deploy. It's done uploading, and I go to Tools, Serial Monitor, and there's nothing. Literally nothing. The TNC cannot send any data out. And this leaves me stumped. So I did a bunch of testing from here. And I figured out that if I changed the sample rate, it would work. So if it was 1 hertz, 1000 hertz, it would work. All the way up to 9500 hertz, which is actually really close to 10,000 hertz. So if you see, if I deploy this code, it'll compile, and the serial plotter will go and show a bunch of data coming out. And that's good. Now, that tells me that the TNC is just a little bit too slow to send all the data essentially. The higher resolution ADC calls are blocking. They don't give the CPU in the microcontroller enough time to send the serial data. That causes it to choke and essentially kill itself. Now, the sensible solution is to buy a faster microcontroller. That's what we did last time. But instead, this is where we make the chip cry. I thought, well, I overclocked my PC to make it run a bit faster. Why can't I do the same thing with microcontrollers? Now, overclocking is a pretty complicated process. It's almost a binary search between what works and what doesn't. It's a lot of skill and precision. Okay, 720 megahertz. And with that, we're done. Yeah, it was just a toggle. So now if we set it to 10,000, it's going to compile. Take quite a bit longer to compile. Did it just crash? Okay, so now if it doesn't crash, we have it set to 720 megahertz, a slight overclock, and now it's going to compile and upload. And now if we go to the serial monitor, we see data coming out. And now we have successfully gotten everything to spec. From there, everything else was somewhat simple. I implemented a serial interpreter, essentially a command line interface from Edgar Bonnet, and customized it for my own use. Then I switched the TNC over to dual serial so that I can have one port for sending data purely and another port for sending commands. After that, I made this very beautiful web UI for the TNC so that anyone can control it so long as they're using a browser. Look at how beautiful it is. After a few more side quests, I went and made this. It's a full-on, actually decent looking USB interface for the Potentiostat on the UC Berkeley nanotechnology website. You won't be able to access this as it's a private page for members with login, but I'll be hosting another version on this on my personal website soon. Let me show you how it works. First, you connect to the read port. That's where you get the data from. Then you connect to the control port. That's where you control the TNC from. Then you can set the sample rate here. The default is 10,000. Set the PWM frequency and change the PWM configuration over here. All you have to do is hit start recording and then hit stop recording. And a CSV with your data will automatically be generated. And ta-da! As you can see, we have our CSV with the correct data outside. You can also see all of the times I've tried this in the side over here. This plot shows the ADC readings of all 18 pins in real time. As you can see, there's minimal noise, and each pin comes through clearly.
And with that, we have the basics of the Potentiostat, making this one little chip cry in order to improve blood tests and improve lives. The next step is to integrate the full Potentiostat circuits so that the people working on CNTs can cross-reference their data, and we can put that all together to get the final product.
Links to the code are in the description. A video on how to set up the system is coming soon. Thank you for watching, and there's probably going to be something about genetic algorithms and geometry dash coming soon as well, probably next week. Thank you.